Hi guys, this is the second video in a series of lectures on quantum mechanics and quantum theory. Alright, so previously we've found that we split up the wave function psi x and t into, now I'm just gonna write it as, well, this should be an uppercase psi because it's representing both space and time. And before we represented the separation variables as phi and capital Phi, but now I'm just going to change it into lowercase psi of x and just phi of t, because that's the standard convention and it's what they use in most books. And we found that phi of t, the time evolution of a wave system, is equal to e to the I et over h bar. Alright, and now we didn't really talk much about this though. We didn't really talk much about that. This has a special name to it. These are called stationary states, because although this is a wave function and is broken down into a spatial and a time component, when we take, let's say, the probability density, which is just psi of x and t squared, the magnitude squared, or the modulus squared, you can say, this is going to be equal to psi times psi star, where psi star is the complex conjugate of psi. And if we take this mod squared, also known as the probability density, we get psi star, that's this term right here, and then we said that we can represent psi as this psi of x and phi of t, but we don't know psi of x, right? So this is just psi of x over here, starred, and then we have this phi of t, which we know is e to the I et over h bar, correct? And now we just have the regular psi of x, and we have e to the minus et over h bar, because when you take the complex conjugate of an imaginary number, you negate it. Complex, notice. And notice also that this term and this term cancel out. I et over h bar minus I et over h bar is equal to 0. So we're just left with the mod squared of psi, the original capital wave function, is equal to just psi star psi of x. So you can see this is pretty important, that the probability density mod squared is only dependent on space. It is not dependent on time. So that means whether you have an arbitrary wave function with some crazy time evolution, crazy space evolution, same time evolution, I et over h bar, the probability density does not depend on this. So the probability density will stay the same as you go along time. Essentially, time evolution does not affect probability distribution. What I mean by probability density, usually call it rho of x, and see it's x, not x and t. And it's usually just a graph, and there's a certain behavior. Let me just draw it a little better. Good enough. There's a certain behavior on probability densities, because since it's a probability density, it shows where we have the highest probability of finding the wave function at any given interval. So just an arbitrary density, probability density, we have over here is the, let's say it's A and f of A. Rho of A. Rho of A over here. this would be the point at psi equals a, where the probability density rho of a is at the highest point. So you're most expected to find a particle at this point. Now, there are some conditions on the probability density that we'll talk about in a different lecture, but I'm just going to briefly state it right now. You can see that the probability density, if we integrate all of all the surfaces of the probability density, if we integrate over all domain, all real numbers, it's equal to a finite value. Let's call it L. Now this is important because it shows end behavior of probability density, which also in turn shows end behavior of the wave function. A wave function cannot just go to infinity because wave functions exist in a space called a Hilbert space. Hilbert space is denoted by this fancy H. I can't really draw it, but I don't know, it looks something like that. And now Hilbert space encompasses all functions that are square integrable. What this means is if you take the integral for all values of, let's say, a function, which in our case would be psi, square integral means that we're taking the mod squared, it's going to be equal to 1. Basically a definition of Hilbert space. All wave functions live in a Hilbert space. Quantum mechanics has been designed, well, a formal way to teach it is to teach it in a Hilbert space, because it was specifically made to encompass quantum mechanics and the wave function. That means that the wave function, let's call psi, and then this is x, it also has a finite area, which is equal to 1. So it also has a distribution like this, and distributions like this are called Gaussians. Alright, but I'm rambling. Let's get back on topic. So, as I was saying, the mod squared of psi, of the stationary states, we call it, mod squared is only dependent on space, not dependent on time. Okay? And then we can notice, I'm going to introduce something here. It's called the expectation value. In brackets, I mean in arrows. Expectation value, it's not the expected value. Well, it is expected value, but it's not where you expect it's not a probability. It's actually the average. I don't know why they call it expectation value. I don't know who calls it expectation value, but it's called expectation value. It's the average of x over the whole domain from negative infinity to infinity. And the expectation value is given by an integral. I'm not going to write negative infinity to infinity anymore because it's just implied right now unless stated otherwise. So it's an integral of psi mod squared times x dx, which you can write it as integral of psi x psi star dx. Because remember that psi mod squared is just equal to psi star. Okay, and same thing for x squared. It would be the integral of psi x squared psi star dx. And notice that we're squishing this x squared between the psi and the psi complex conjugated. But here, let me show you the p, the expectation value of p, the average value of p over all the reals. This is a little bit different because p is actually an operator. X is also an operator, which we will get to, but x operating on some system, let's say, operators are Hermitian. We'll get into it later, but briefly I could just say that operators act on states which perhaps we could say a state such as psi, operators act on the state to give you an eigenvalue, which we will also get into later, of x. So basically the x operator only gives you the x value, which is common sense. If you act on a function, wave function, with an operator value called x, the space operator, it will give you the spatial point at which psi is located. But for p, it's a little different. The momentum acting on psi is a little bit different, because the momentum operator in quantum mechanics is a function in and of itself. The momentum operator is actually denoted as I over h bar d over dt. I mean, no, not d over dt. Actually, it's, oh wait, it's not even I over h bar. The momentum operator, the momentum operator in quantum mechanics is denoted as h bar over I times the partial with respect to x. Because remember, p equals mv from classical mechanics, so velocity vector, m is a mass, it's only dependent on x. So it's a little bit different. Now, the expectation value of this momentum is going to be the integral, same thing, psi, but now instead of x squared as we have here x squared, we're substituting p equals this, so it will be h bar over I dx, and then psi star dx. And we can simplify this a little bit because we can bring out the constant h bar over I out, integral of psi, and then now the regular derivative of psi star dx. Okay? So basically the same thing, not that hard. And this is where we can generalize it at this point. We can generalize it for some arbitrary expectation value, let's say q. And it can be a function of x or momentum. Depends on either if you have the expectation value of x or the expectation value of momentum. You take either the x1 or the p1. It's defined to be equal to the integral psi as we had before, and now we have this q, which is operating, and it could be a function of x, or p, which I said is h bar over I partial with respect to x of psi star, and then dx. So this is the generalized one. This is the one that you should know. Okay? And every expectation value is constant in time. You see, there is no time dependence in the expectation value, as there was no time dependence in the probability density as we did before.